let's start. So today we have the creators of Hathor blockchain. So it's a high performance blockchain. The architecture and the data structure is different from what we have with Ethereum and Bitcoin. So they will make a full presentation about blockchain, how it works from the inside. I think it's, as I said, a unique opportunity to talk with people that developed a real blockchain. They are the best source of technical information we can have. So, Marcelo, feel free to go ahead. I will stop sharing my screen and then you can start sharing your presentation.
Yeah, thank you very much, Carlos. And I like to say hi for the people from MIT and NIU and all the others that are here watching us. It's a pleasure to be here. And let me share my screen so we can start. We have a lot of topics to cover today. So it will be a long journey inside the blockchain. Can you see my presentation?
Yes, we have.
It's working?
Yes.
Just change the slide and get back. Okay, I guess it's working. So may I start?
Sure, go ahead.
Okay, so hello everyone. Thanks again for being here. It's a pleasure to talk to you. And if you have any questions, please interrupt me and let me know. We have a lot of things to cover today. I can't really see the chat part of Zoom. So now I can. So I guess I can read your messages if you send, and maybe I can hear you. So please, I'll kindly ask Carlos to help me to coordinate if I can't see any of your questions. So my name is Marcelo. My background is in computer engineering, and I did my PhD in blockchain and in artificial intelligence. And the blockchain part, I studied scalability of blockchain, and that's where Hathor was born. Hathor is a scalable blockchain with a new architecture, different from other blockchains. And here we will dive deep into the blockchain world. We understand a blockchain from inside, and you will understand how Hathor is different from the other technologies that we have in the market. This lecture, this conversation will happen in two parts. This is the first part where we will cover basically the blockchain part. So I'm not diving into the specifics of each network, but on our next meeting, I'll definitely do this. So yeah. And you can reach me out anytime. It'd be my pleasure to answer your questions after our conversation here. So let me start. And I guess you are in a class for blockchains and artificial intelligence, and you need to integrate your pitch with a blockchain. So the first question is, how do I integrate my application with a blockchain? And out of this question, the next natural question is, okay, but what is a blockchain? What does this term blockchain refers to? I have to have this understanding. Sorry? Can you hear me? Yeah, I can hear someone talking. And yeah, someone have to mute.
Yes.
Yes. Okay, I'll get back here. No problem. So, so a natural question is, what is a blockchain? What does it refer to? So in a very basic model, wow, I lost. Okay, now it's working. In a very basic model, you have your application, you have a blockchain, you can read from the blockchain, you can write to the blockchain, but what is it? And that's where we're going to start. What is a blockchain? And my first answer to this question is the blockchain is a database. Okay, we have a lot of database available today. We have MySQL, we have SQL Server, we have NoSQL databases. So is blockchain like one of those? No, it's not. Why? Okay, let's go. Let's be more specific here. It's a distributed database. What does it mean? It means that the blockchain, in the blockchain, the database is distributed among several servers. It's not only one point, it's distributed in a network. And then you can think, okay, we have clusters, we have a sharding, we have several different types of distributed data today. Is a blockchain like one of those? Oh, no, it's not. There's more. Besides being distributed, a blockchain is decentralized. And what does it mean? It means that a blockchain runs in a network because it's distributed, and this network has no special peers. There's no centralization, there's no primary nodes, there's no master nodes, there's nothing like this. Each peer in the network is independent, and they make decisions by their own. And in fact, they don't trust each other. We'll definitely dive into this concept along this conversation today, but besides distributed, it's decentralized. And it's not just that. Besides being decentralized, it's immutable. So what does it mean? It means that after you write something to this database, and this data is confirmed by the network, as you see, the data cannot be deleted or changed afterwards. It's impossible to do it, and that's one of the main questions of this conversation. How? Usually, immutability is something that we can achieve from centrality. If you have a central point of trust, we can try to create immutable data. But in this case, our database, it is distributed, decentralized, and immutable. And with these three features together, blockchain is a unique technology. So how does it work? Just a quick recap. We have a network of computers all around the world connected in a network. The database, the data is stored in the database is distributed. Every peer has its own copy of the database, or as you say, each peer has its own copy of the blockchain. It's decentralized. No peer trusts each other, and they don't have to. There's no coordinator. There's nothing special for each peer. They are all the same. And in a public network, in a public blockchain, you can run your peer and you'll be just like the others, just the same thing. And it's immutable. After you write there and it's confirmed, you cannot change it. So getting back here to our very simple diagram, a blockchain is not like a block like we're seeing right now. We have a better understanding of how it works. In fact, a blockchain is a network where many computers are connected to. And what you do is that you cannot read or write from the blockchain. You can run your full node. Your full node participates into the network. See, it's connected to some, I don't know, can you, you can't see my mouse, right? Yeah, okay. So the full node is connected to some peers of this network, and the peers are connected among themselves as well. And you can read and write from your full node. That's an important piece, and it will have a lot of consequences as we'll see later. So that's our current model. So let's see how it works a little bit more when we try to write something into a blockchain. So the write operation, it's quite simple, right? We have a data that we'd like to write, and then we write to the database, let's say to the blockchain. In this case, we send it to our full node, and it returns an ID for us, a transaction ID. What happens inside is that your data is encapsulated into a transaction, and the transaction is pushed to the network. And then after the transaction is pushed to your full node, it validates in the validator. Then a consensus algorithm runs. We'll see what it is. It's stored locally. And then the synchronization model is responsible from connecting and syncing, keeping all peers in the network synced. having the same copy of the database. And the peer-to-peer network model will relay your transaction to all other peers. And then the peers will relate to their own peers and so on until every computer in the network has a copy of your transaction. That's a right operation in a blockchain. We will see a little bit, much more further how it works. But going to the read operation is quite simple. You have your full nodes. See, there's no blockchain anymore. You read from your full nodes. So it means that your application must trust your full nodes. If there are several public full nodes available in the internet for different blockchains, if you use one of those full nodes, they can be lying to you. They can be tampering data. So the best way to read is that the most safe way to read is that you run your full nodes, you get the information from the blockchain, and then your application can read from your full node. But what's reading is about, usually, you give the transaction ID and it returns usually two pieces of information for you. The transaction itself, which is immutable because it's been confirmed by the network, and also a metadata. This metadata changes over time, and it may be, for instance, whether the transaction is confirmed or not, and other things. Yes, as we go, it will be more clear what comes from the metadata, but usually whether a transaction is confirmed or not, okay? So the next nature question is, okay, I'm telling you that transactions are immutable, but how? How does the network do it? And here we start a journey inside the blockchain technology. And so let's go. I have no feedback here. I just like to confirm that you can hear me properly so I can start it.
All good so far, Marcelo.
Oh, perfect. Thank you very much, Carlos. Sure. So let's go. Well, the primary goal of a blockchain is to solve conflicts. That's the first concept that's very important to understand how a blockchain works. So two or more transactions, they might conflict. And here I'm talking abstractly. I'm not giving specific definition because it changes with each network. So for example, in Hathor and in Bitcoin, transactions are in conflict if they are spending the same money. You understand what it means? But let's say that money is in the email. So what? Maybe I can get.
Marcelo, can I just make a break here?
Sure.
So that's the most important information we got so far. What is a blockchain? It's an engine to solve conflicts. That's the definition of a blockchain. It's an engine to solve conflicts. Whatever is the definition of conflict, that's what a blockchain is. It's an engine, it's an IT engine built to solve conflicts. And what Marcelo is telling is a conflict under the definition of Bitcoin is a conflict is a double spend, and that's all. That's the definition coming from Bitcoin. So people cannot spend the amount of Bitcoin they have twice. But at the end of the day, a blockchain, it's a technology engine to solve conflicts. And that's all. Okay? Yes.
I think the most important conflict there is the Byzantine protocol and the theory of games.
Yeah, Marcelo will go over that in a few. Yes, you're right. Thank you, Marcelo. Sorry for the interruption.
No problem at all. You can interrupt as you wish. I couldn't hear the question. I just heard what you talked. And yeah, I'll talk a little bit about Ethereum. Ethereum has a different understanding, but yeah, Carlos, thank you very much for pointing that out. A database, it might have conflicts. So I don't know, someone tries to change a name. So there are two records with different names. Which one is valid? And the definition of conflict changes. And the blockchain basically is there to solve this, to get a resolution and decides which information is true and which information is not true or is not valid. Ethereum is a different animal from Bitcoin and Hathor. It's in Ethereum, transactions are basically execution of methods. It's running a software, and a conflict in Ethereum is when two transactions or more cannot be all executed. If one of them fails, that sequence of transactions is represents a conflict. But we'll see it deeper when we talk about Ethereum. So the first thing here is the primary goal of a blockchain is to solve conflicts. So the next natural question is how? How does a blockchain solve conflicts? And in this journey, our first actor here is the block. What is a block in a blockchain? It's basically a set of transactions. So a block has a set of transactions, let's say inside it, but not necessarily. A block confirms a set of transactions. That's it. It represents a set of transactions. But there's more. Besides representing a set of transactions, a block must have one parent and only one parent. And then it forms a blockchain. So here we can see some blocks. Block 1 has 4 transactions, is confirming 4 transactions. Block 2 is confirming 1 transaction. So the number of transactions doesn't matter. Block 4 is even confirming 0 transactions. It might happen. You might question, why would such block be created? And I'll give you the answers, this answer in a moment. So basically, now we know that a block confirms a set of transactions, and a block also has one parent block. It forms a blockchain. And there's one rule. Blockchains cannot have any conflicting transaction. So in this example here, the blockchain formed by the blocks 1, 2, 3, 4, and 5, this blockchain is invalid because I'm telling you that transaction A and transaction B are in conflict, so they can't belong both to a blockchain. If it happens, this blockchain is invalid. So in this case, the blockchain could have none of them, no transaction A, no transaction B, or either one of them, but not both. That's the rule. And that's a very important rule because that's part of the conflict resolution mechanism. But now that we have blocks which have parents and create blockchains, we can have 2 blocks just like A4 and B4 pointing to the same block, A3. So in this case, we say that blockchains might fork. And we, in this structure here, we have several blockchains happening. See, we have the blockchain B4, and I'm using the last block as a the name of the blockchain because we can just follow the trail. So B4, A3, A2, and A1, it forms a blockchain. But another blockchain would be A5, A4, A3, A2, A1. Another one would be C6, C5, C4, C3, A2, A1. So multiple blockchains might exist. D5, C4, C3, A2, A1. And between different blockchains, there might be conflicting transactions. See, blockchain B4 is valid. It has transaction A. Remember, transaction A and transaction B are conflicting transactions. But B4 is valid because there's no transaction B on its chain. But on A5 blockchain, transaction B is there. It is still valid because there's no transaction A on the A5 blockchain. The same for blockchain C6. Transaction A is there as well. And on D5, there's no transaction A and no transaction B at all. So here we get to a very important moment in the blockchain. How do we know which blockchain wins? How do we know whether transaction A is executed or transaction B is executed? Because both of them, they cannot be both executed, just one of them. And here comes the consensus algorithm. The consensus algorithm makes the decision of which blockchain wins. And there are several different types of consensus algorithm. And in this conversation here, we'll focus on the proof of work consensus algorithm. And we'll focus on this one because it's the one currently used by Bitcoin, by Ethereum, and by Hathor. Okay, but there are others. Other blockchains use different consensus algorithm. So what is the proof of work consensus algorithm? Well, the proof of work was created to control maybe span, but it has several uses. It failed for span control in email, but the proof of work is a mathematical problem. It's a mathematical problem that must have some features. The first one is that it must be hard to solve. So it must be something that is hard to find a solution to. It must be easy to verify the solution. It must be deterministic, which basically means that if I have found a solution, you check and you confirm that it's a solution. It cannot be something random, something stochastic, cannot be. And it's very important, it must be a difficulty parameter. So we can control how hard it is to find a solution. Let's say that we don't have computers. We have to do all by hand. Polynomials might be a candidate for a proof of work problem because it's not that easy to find the roots of a polynomial, but it's easy to verify. If I give you the roots, you can easily verify. It's deterministic and it has a difficulty parameter, let's say the degree of the polynomial. But computers can solve polynomials and polynomials are not the choice for our proof of work here. A very common function used for proof of work is the hash function. So what is the hash function? The hash function is a function, a mathematical function, that there's an input. The input is a sequence of bytes, and it brings a point in the range, in a given range. In this case here, n is the number of bits in that range. So between 0 and 2 to n minus 1. So if n is big, let's say 256, that's a huge range. And the hash function has some characteristics. If I give the same inputs, it always gives the same output. So it's deterministic in this sense. But if I change one bit, only one bit of the output, it's completely unforeseen where the new point will be. So, and this new point follows a uniform distribution. It's as likely to be in any point in that range, which means basically that the hash function is random when I change the input, but when I give the same input, it's deterministic. It gives always the same output. And what is the problem that we must solve in this case? Well, let's say that we have an A, and we want to find an input, a sequence of bytes in which the output of the hash function is in the range from 0 to A. As it's an uniform distribution, the probability of the hash of the function be less than A is A divided by 2 to n. So here A is related to the difficulty. When A is big, let's say A is in the half of the range, half of the times, because it's uniform, we will have points on each side. If A is really small, the difficulty increases. It's more likely to find points out of the 0 to A range than into the 0 to A range. And that's the problem. So the difficulty is proportional to the inverse of A. That's how a hash function works. And how are we going to use it? Well, that's the mining problem. That's what miners are doing. Miners are looking for an input to the hash function, an X, such that the hash of this number is less than A. So what happens here is that they put a random input and they look, okay, it's gray dots. Let's try again. They change the input +1. And then another gray dot, okay, +1. Another gray dot, okay, +1. Another gray dot, and then, okay, +1. They found a green dot. The green dot is between 0 and A, so they found a solution. That X is a solution. So the X is this random variable of how many tries do I do to find a solution. And it follows a geometric distribution. And the expected number of attempts is 2 to 10 divided by A. And which basically means that when as we saw before, when the A grows, the expected number of attempts reduces. So it's easier. When A gets smaller, the expected number of attempts increases. So it becomes harder. A is our parameter of difficulty. And this kind of geometric distribution, it's very important because it's memoryless. So let's say that I started looking for a solution and I've been here for 1 hour trying and I couldn't find any so far. And then you say, okay, let me try as well. So it's fair for you because the fact that I've been trying doesn't give me any advantage. So we have equal, if we do the same number of attempts, we have equal chance to find a solution. So it's fair for the miners. And using this proof of work, we say that all blocks must be mined, but what does it mean? Well, from the block, we can generate a header, which is basically a sequence of bytes. This sequence of bytes has announce, which is a number that you can put anything there. It's just a number. It has the difficulty. So how hard is from the difficulty, we can calculate A, but how hard it is to find a solution for the hash of this block. We have the parent block there, and we have the transactions. I'll get back to it in a minute. So what I do, I get the block, I generate the header, I get the header, I put into the hash function, and I change the nonce. So I get a gray point. I change the nonce again, +1, I get another gray point, +1, another gray point, and then until I have a green point. This nonce that gives me the green point is the solution to this block. See, we have to work to find the solution of this block. And that's exactly the terminology that we use. The work that you have to do is proportional to the expected number of trials, of attempts that you have to do in order to find a solution. So when we decreases the value of A, we need to work more because more steps, more trials, more attempts are necessary. And let's say that after I found a solution, so I know the nonce that gives me the green dots. When I send you the nonce, any of you can easily check. It's very fast. You calculate the hash, and you see that the value of the hash is less than A. So it's very easy to check. But let's say that and here we come to the first moments of immutability. Let's say that you go there and you change a transaction. See, the transactions are inside the header somehow. So if you change a transaction, then that nonce wouldn't be a solution to the hash function anymore, and the block would not mined. So if I'd like to change a transaction here, I'd have to mine the block again. I have to work again. That's the first part of immutability. That's not the end of it. There's more, but that's the first part. So if I try to change the difficulty or the parent block or any transaction, I have to redo this work. I have to find another solution. I have to find another nonce. So I have to work. And now that we have the concept of work from a block, we can extend this concept to calculate the total work of a blockchain. So the total work of a blockchain is the sum of the work of its blocks. Here I put some float numbers, some numbers here in parentheses that refers to like this work of each block. Usually it's not a floating point number, it's just an integer. It depends on each network. It's just an example here. So let's say that on B4, we have A1 plus A2 plus A3 plus B4, 12.7. For A5, the total work of the A5 blockchain is 3.2 plus 3.5 plus 2.8 plus 3.2 plus 5.7. That's 18.4. And what happens in this proof of work consensus algorithm is that the one with the highest work wins. And we call it the best blockchain. All other blockchains are voided. They doesn't matter. So in our example here, A5 is the winner. So we can say that transaction B is confirmed. Oh, what about transaction A? It's not confirmed. All the other blockchains, they don't matter. Just the best blockchain matters. That's the winner, and that's the data that we can trust. That's how the consensus algorithm solves the conflict. Because in a blockchain, there cannot be any conflict. Okay, it's conflict-free. And then you can ask, wow, so we have to keep mining blocks in order to confirm in order to decide how to solve the conflicts? And I'd say yes. And it's a lot of things to be done, a lot of work to be done. And I'd say, you're right. Why would anyone do that? And that's a very important question when it comes to blockchain, to the incentives. Well, one would do it because they receive to do it. We say that the network pay miners through usually two sources. Mining rewards, what does it mean? Every time a new block is found, you can create some tokens for yourself. So let's say that you're mining Hathor blocks. When you find a solution to a block in Hathor Network, the networker comes and say, okay, it's okay for you to create 32 Hathors for this block. We're giving it to you. So it's a kind of an inflation happening as you are creating tokens. That's the same for Bitcoin. That's the same for Ethereum. Whenever new blocks found in the Bitcoin network, people receives mining rewards, which basically is new Bitcoins. So we are paying miners to work. That's the incentive part. Besides the mining rewards, depending on the network, there might be some fees. Transactions might pay fees, and the miner can collect those fees for him. So that's another source of income. Okay. The incentives in a blockchain are a very important topic, but I'll go forward. We have a lot of other things to discuss. The natural thing about here is that you can say, okay, so I'll mine as well. The problem is there, I'll try to solve it myself. And the more people are looking for a solution, the more blocks we'll find, right? If we have more people trying, we have more attempts per second, then more blocks will be found. That's correct. And that's why the difficulty of the proof of work is important, because we have the difficulty adjustment algorithm, which basically is a control system which tries to keep the time to find the next block in a range. It has a target. So whenever more people comes to mine, more people comes to find the solution to this problem, the difficulty, the DAA increases the difficulty. So it becomes harder and it takes longer for people to find their blocks. Let's say that the target is just like in Hathor, 30 seconds. So if people join to start mining, to keep mining, what happens is that they will start finding blocks more often. And then the DAA goes there and increase difficulty until this average time gets back to 30 seconds between blocks. So one must work, the whole network will work together for 30 seconds to find the next block. And if miners stop mining because they don't want to do anymore, then the number of attempts per second reduces and it takes longer to find the block. So if it takes too long to find the block, the DAA reduces the difficulty and then you can find the block faster again. Here in this chart, we have the difficulty over time in the Bitcoin network. So you can see that it changed a lot. From 2016 back, it seems to be zero, but it's not. It's just really small compared to the nowadays. But here, after 2020, you can see this plummet. And this plummet is when China prohibited mining in their territory. So a lot of miners had to stop mining and the difficulty went down a lot because it took longer to find the block and then the DAA corrected it, make an adjustment. And here we have an opportunity to explain a very simple and common attack to new networks, which is called the stalling attack. So let's say that you control a lot of hash power. So what it means that you can do a lot of attempts per second. So you go to a new network, you start mining that network, the difficulty increases, difficulty increases, difficulty increases, it gets really high, and then you leave. And then all the miners together, they can't find the next solution. It's too hard. And the DAA needs new blocks to adjust the difficulty, so the network stalls. It has happened to many blockchains. You can check it there, and there are quite a few solutions for that. But I'm not entering into this here. But that's basically how the DAA, how the DAA controls the rates of blocks. In the Bitcoin network, usually they are looking for a target of 10 minutes between blocks. So it doesn't matter if more people or less people are mining. What happens there is that the DAA will try to make sure that there are 10 minutes between blocks. That's a target, a parameter of the blockchain. Wow, okay. So we dove into how blocks and what are blockchains and etc. So let's get back and remind where we were and what we're trying to understand. We're trying to understand how transactions are immutable, how we can create immutable transactions in this database, in this network. And so what happens when you create a new transaction? So I'll repeat it over, but with a lot more details for you, is that the new transaction, your data is encapsulated in a transaction. This transaction is sent to your full node. Remember, there's no such thing as a blockchain. There are nodes, peers connected in a network. Your full node validates, check the consensus. Now you know what it means. It's checking whether that blockchain is valid, not valid, conflicts, etc. If everything is good, the transaction is relayed to the other peers, as you can see in the right. It's sent to the network, it's relayed through the network, and the peers will do the same thing. This full node diagram here, it happens in every peer of the network. But the full node also saves these new transactions in a special area called mempool. The mempool is the set of transactions out of the best blockchain. So they are waiting to be confirmed. Those are the transactions that might be in the next blocks. Remember, the blocks can choose, they can pick which transactions they'd like to confirm. It's their choice. So what happens is that miners are the ones who does it. Miners, they create what we call a block template, which is a block, but it's the proof of work of the block is not solved. So the block is not valid right now. They still have to find a solution to find the block. So we call it the block template, where they choose from the main pool, usually, which transactions will belong to that block. And they have what we call a hash rate, which is the number of attempts to find a solution to the proof of work that they can do, that they can perform. And they keep trying, they try to find a solution for the block. So they change the nonce, check the hash, dot green, grading, gray dot. So not a solution, try again, until they found a solution. But it's important here here comes another incentive of the network. The miners can cherry pick, they can pick whatever transactions they'd like to put in the next block. Which ones would they get? Usually the ones which pays more fees because they want to profit out of it. So usually miners, they have algorithms to decide which transactions they put in the block and which transactions they won't put in the block. So if the network gives the wrong incentives for miners, they can just stop or they can just skip your transaction. And here comes one point that's interesting. Whenever an attack is happening, usually exchanges and different players in the blockchain world, they get in touch with the miners saying, please skip this transaction for me. It might happen. It has happened before. So we start to understand the dynamic of the network. But I'm not going to text right now. We have time to discuss it later. So the miner gets the transactions from the main pool, builds this block template, decides which transactions it's mining, it will confirm, and it keeps mining. When a block is found, when the solution is found, then the miner push the block to the full node, send the block to the network. Again, the same steps happen. The block is validated, the consensus is updated, which means there's a new block in town. So what do we do? Is it the best chain? Again, is the new best chain? Is it orphan? Is it voided? I don't know. Then if everything is okay, the peer-to-peer network relays the block to the other peers on the right, and it happens again and again in all peers of the network. So the block is relayed to the other peers and propagated through the network. And here comes the answer. A transaction is immutable, cannot be deleted, cannot be changed. Why? Because it's more and more expensive to change it. As new blocks comes to the network, it's more expensive to change it, because let's say that we have a transaction on A3 and we say, okay, maybe I'd like to change or remove this transaction. I'd like to change this transaction. What do I have to do in this network? Okay, you can create B3 with a new transaction change, with this transaction change. You're trying to change the data. But now you have to find a solution for B3. You have to mine B3. After B3 is mined, you can say, okay, I found a solution. And now, and I say, okay, B3 does not have a higher, the blockchain B3 doesn't have a higher work than the A6. So B3 doesn't matter, it's voided. The network keeps with A6. And then, okay, so I can go for B4 and find a new block, and then B5, and then B6, and then B7, until the total work of the B blockchain of B7 is higher than A6. And if you can do it, then you can change the past. But you are fighting against all the other miners. You are fighting against the network. And it's very, very expensive to keep a mining operation. That's why we say that a transaction is immutable, because it's so expensive that nobody does it. But if you can spend the money to have access to a higher hash rate in the network, and you have more than 50% of the whole hash rate of the network. The hash rate, again, is the number of attempts per second to find a solution to the proof of work. Then you can create this new chain. And if it happens, we say that there was a reorg in the network, because the best chain changed considerably. And that's usually a problem. But in Bitcoin, as far as I know, it's never happened. Maybe I'm wrong. As far as I know, it's never happened. But that's how it works. So it's not that the transaction is immutable, in fact, but it's so expensive that we consider it immutable. That's how it works. And here we kind of finish this understanding of how a blockchain works inside, how the consensus algorithm decides which blockchain is valid, which blockchain is the best blockchain, and that's how conflicts are solved in a blockchain network. And here comes a quick quiz just to discuss. We have way more to cover here. Let me just check the time. It's 10. Okay, 45. Okay, 9:45. So let's go here a bit more, and then we have a little break. I guess it's 15 minutes more, right, Carlos?
Yeah,
break. About that. Okay. So here, quick quiz. Okay, can a transaction A be in the mempool in this case? Let's say that you have these blocks. A5 is the winner because this one is the one who has the highest total work, the sum of the work of the blocks, and it confirms transaction B. And let's remind that transaction A, transaction B are in conflict. So can transaction A be in the mempool?
Yes.
Can transaction A be there? And here it's a tricky question because it depends. It depends on who you are. Remember, the network, it's distributed. We saw the whole network. We are relaying blocks and transactions all the time. So the whole network has copy of the blocks and transactions. It's decentralized, which means there's no central point of coordination. And that's why it's tricky. Because if you have a copy of the whole blockchain and you conclude that AI is the best chain, and you are an honest node in the network, then no, transaction A cannot be there in the mempool. because transaction A is in conflict with transaction B. And if A6, and let's say that A6 is the next block, confirms transaction A, then A6 would be invalid because there would be a conflict in the blockchain and it's not allowed. So if you are an honest peer and you are in the network, then and you have everything, you have all the data here, no, transaction A shouldn't be there. But let's say that you just connected, you are downloading the blockchains. You are not there yet. And so far you don't have the A3, A4, A5 block, but you have C6. So for you at that point in time, C6 is the best chain. So there's no need to have transaction A in the mempool. It's already been confirmed for you. But let's say that you are, there's another peer which is downloading the blockchain in a different order, and they have D5 just. They don't have the other blockchains. D5, C4, C3, A2, A1. So this guy, this peer, for this peer, yeah, transaction A could be in the mempool. Either A or B, but not both. So each peer makes their own decisions, how they want to do it. But after all these peers finish downloading, syncing, how we say, after they finish syncing and downloading all the blocks and all the transactions, they will all reach the same consensus that A5 is the best blockchain, transaction B is confirmed, and transaction A is not confirmed. And that's what brings, that's what makes blockchain a unique thing. Because after everyone has the same consensus, exchanges can trade, can start trading, can accept deposits in that blockchain specifically. Because only the transactions in the best chain are the valid ones. All the others are not. So from this point, when the network reaches a consensus, we can start building companies, we can start building business over a blockchain. And that's why it's safe to do it, because everyone has the same consensus. Some notes about mining. I guess it's a good time to make a break. So, and then we can continue later. So you can rethink about everything we said. There were a lot of concepts. And before the break, we have a few minutes here. So I'd like to open for questions so I can get back so you can really understand how it works. We have a lot of nice things to discuss yet, but let's do it now.
We have a question here, Marcelo. Can you go back one slide?
Sure. Here?
Yeah. So my question is, the reason why we are using A5, right? And that means that transaction B is the one that is going through because it's in conflict with A and it's the best logic, right? But this is because the two transactions are in conflict.
I'm sorry. I can't hear you well.
I'll repeat it to you, Marcelo. I'll repeat the question to you. Hold on.
Okay.
My question is, if there's a transaction in, let's just say, C4 that is not in conflict with the transaction in A, it's still, I mean, it's not in the best blockchain, but it's still like valid, it's still going through.
So the question is, let's say that we have a transaction with no conflict with transaction B.
Okay.
Is the C6 network valid? A valid blockchain. So let's say that we have no conflict in the mapping that you're showing, and we have this fork. So the question is C6 a valid blockchain?
Yeah, I mean, here, let's just separate two things. There's valid blockchains, invalid blockchains, but there's also the best blockchain. So let's say that we have a transaction in C6, which is just on C6. It's not on any other block. That's what I understood. But it's there. But C6 is not the best chain. The best chain is A5. What happens in this case? Is that the question? Did I get it right?
Yes. It's let's say that we have no conflict on the mapping you're showing.
Yeah,
So
just
how can we define that A5 is better than C6, for example?
yeah, exactly. A5 it's not a matter of being better; it's a matter of a definition. We consider the best chain the one with the highest work, the one in which people work more. So let's say that that's how the consensus work. So A5 is the best chain because of that. But if you have a transaction on C6, let's call it transaction X. This transaction X, in this, if you have this situation here, it would be in the mempool. Because let me get back to the definition of the mempool. The mempool is the set of transactions out of the best blockchain. So what happens is that, let's say that you are here, you have C6, you don't know A5 yet. And then you're syncing, and then you receive the A3 and 4 and 5 blocks. And then you change, right? Your best chain changed from C6 to A5. What happens to those transactions in C3, C4, C6? The ones that are confirmed by A3, A4, A5 will remain confirmed. What about the others? All the others get back to mempool. And then eventually A6 will confirm one of those transactions because they are conflict-free, so they can be confirmed. So what happens is that the transactions that are not part of the best blockchain, they are always in the mempool. They are always available for miners to put them on the next block.
Yeah. Okay, thank you, Marcelo.
No problem. Any other question?
Yes, we have another one.
Yeah, so let's say if I transaction, but there is transaction in C3 that a miner already mined, so in work has been done here. But because if is the blockchain, the transaction in C3 would have to, so another miner would have to rework on the transaction in C3.
Yes, that's true. It will be waiting till we get the confirmation on the best blockchain.
Those transactions would have to go again, and
Yeah.
there would be another work.
Yes, yes. At some point, they are on the mempool, and at some point, they will be confirmed, and they go. They will be a part of the last block of the blockchain.
No, yeah, perhaps there's later, but what happens when that one, like goes to C6, became like, yeah, became a whole, like he considers himself like as network, and he just replicates from the original network. When the fellow is the most successful algorithm.
So the explanation is like there is a difference between the best blockchain and a conflict. A conflict should be vanished from the blockchain. We cannot accept a conflict. That has to be eliminated. But if there is no conflict, it means, and we have a fork, it can happen. But it means that the blocks that are on the fork are just on hold till they became part of the best blockchain.
Yeah, but sometimes like there's a myriad of examples like Ethereum with the Ethereum Classic, Bitcoin with Bitcoin Cash, and then Bitcoin Cash with Bitcoin HTC. So they decided to create their own network with a couple of other transactions that were mined, but we're not deep like the best ones. But they like a rather a group of miners, they consider themselves, okay, we do have the best network here, and then we just split from the original.
But that's no longer, at the point they split it, it's no longer the same blockchain.
Yeah.
That analysis is inside a blockchain.
Because they were managed. Right?
Yes, it's outside. Okay, Marcelo.
Yeah.
We can have a 5 to 10 minutes break now. So, and people will be back for your surprise. I didn't tell them about what the demonstration you're going to do on Hathor blockchain, so they don't know exactly the surprise you prepared for them. But we can go after a 5 to 10 minutes break. Okay?
Yeah, sure. Just one point. I couldn't hear all the conversation you had. Just one point that the blockchains that are not the best blockchains, the ones that are voided, they are still valid, but the transactions there are just not considered confirmed. Okay, so they are valid, but they are not the best blockchain, and only the best blockchain matters.
Okay.
Yeah, there's an error. There's a mistake in this diagram here. From C5 to A5, it's wrong. I'll get it out. Sorry.
Okay.
I'll fix it later. Okay, so let's go for the break. In 10 minutes, we return for notes about mining. And there's a lot of attacks to discuss, a lot of things, so you can get a better understanding of how the network handles attacks and situations. Okay?
Okay.
Thank you. So we'll see you in 10 minutes.
Yes, I'll mute myself and remove the video, and I'll get back to it in 5 to 10 minutes.
Okay, yeah, I'll be back in 5 minutes. I'm here again.
Okay.
Thank you.
And then, for example, I also have this one, and that's because I'm part of the graduate student council. It's like they add courses as part of like other things. So it's something that we can do. Yeah.
Hi, Marcelo. We are back. As soon as you're ready, we can restart.
Okay, thank you. Yeah, I'm good here. So let's get back to where we were. Just 1 second. You can see my screen, right? Whatever I open here, right? Okay.
Yes. Yes.
Yeah, I'll need it in a minute. So, okay, so a few notes about mining, and these notes they have consequences for security and different stuff, and we get a better understanding of the dynamics of the network. So just to confirm, you're hearing me well, right?
Yes.
Okay, perfect. So some notes on mining. Okay, mining is a random process, which basically means weird. There's something on my other screen. Sorry, let me just see how to get it out. Here. Okay, now we can see it better. There we are. So mining is a random process, which basically means that we are there trying, and the time to find the next block follows an exponential distribution. And why it matters? Because even if the difficulty is appropriately fixed, if the DAA is working nicely, there's a lot of variability in the time to find the next block. So as you can see, let's say that the time to find the next block is just like in Hathor, so 30 seconds between blocks. What this random process explains to us is that 63% of the blocks will be found in up to 30 seconds, but a lot of them will be found in 1 minute, in up to 1 minute, and several of them might take even 2 minutes. So it's kind of safe to say that 98% of the blocks will be found in up to minutes. So the time between blocks will change, and after a block is found, it must be relayed to the network. And I'll get back to this in a second. Well, trying to change slide here. Okay. So what happens is that, let's say that I'm mining and I just found a new block. So I get the block and I push to the network. But as we know now, there's no such thing as a blockchain. There's a network of computers. So the block will go to the my full node. And then my full node will relay to the network. But it's not something that happens instantly. Our my full node has to change, to send the block to one of its peers. So let's say that the first one here on the top just received it. And then it will check, it will verify, it will confirm that the block is valid, it will check the consensus, all the things that we know, and then it will relay to the next block, the next peer, and so on. So it takes a while for the block to be available in the whole network. And this time to propagate new blocks, it's a problem for miners, because the miners are in the business of finding the next block. They want to collect the fees, get the reward mining, and move to the next block. So if their block is not in the best chain, they are basically losing money. They are wasting resources and they're losing money. And as blocks takes a while to propagate, this kind of situation happens every time a new block is found. While the block is propagating through the network, there might be updated miners which have already received the new block. And they will be mining on block templates, updated block templates, and will be mining correctly, let's say. But there might be outdated miners, which basically means that their full nodes haven't received the block yet. It's still relaying into the network. And they are mining out of from block 4 instead of the new block because they don't know the new block. And in the meantime, while the block is propagating, these outdated miners, they can find a solution. It's a random process. And when they find the solution, that's the situation we get. They find another block. So I put the blocks here in orange because now the consensus is a bit divided among the peers in the network. The peers that have received the new block thinks they agree that the consensus is in the new block. The best chain, the best blockchain is the new block. But that outdated miners, they found a new block. There's another block. And for them, that's the best blockchain. And they are also relaying their block to the network. And the network at the end, when it finishes syncing, when it finishes propagating both blocks, the network will have the new block and the another block. In our example here, let's say that the new block has more work, so we can find what will happen. What will happen is that what we call the outdated miners, they will receive the new block eventually. When they do, they will start mining out of this new block because that's the new best blockchain. And what about the another block that they found? This block will be what we call an orphan block because it won't be part of the blockchain. And all the resources that were used to mine that orphan block are lost because the miners will not receive the reward mining, the mining reward. And okay, here I might be a little bit impressive, not because Ethereum gives some reward for orphan blocks. So there's a structure to do it, but let's just talk generically. Miners, they lose money when this kind of things happen. So in this perspective, you can get another understanding of the mining business. The mining business is about mining on the best chain. And just as an example, Bitcoin network is a very big network. We don't know how many peers are in the network. It's not something public because the network is decentralized and there's no coordinator. So we don't know how many peers are there. The peers are independent. They can work as they wish and they can choose to whatever peers they would like to connect to. But it's estimated that Bitcoin network has more than 100,000 peers. And there's a work from, I guess, 4 years ago, which they tried to measure the time to propagate a new block into the Bitcoin network. And it took around 42 seconds to be sure that the block has reached all the peers, or at least more than 98% of the peers. I saw some study, more recent study, in which this time reduced to, I don't know, maybe a few seconds, 10 seconds, less than 10 seconds, I'm not sure. But while this block is being propagated, orphan blocks might happen. And it's an honest mining, right? This outdated miner here, it's an honest miner. It's not trying to trick the network. It's not trying to attack the network somehow. So we can conclude that orphan blocks are a natural consequence of the mining activity, but it's very bad for the miners because they are wasting money, okay? And if we model, it's not okay. If we model what's the probability of finding a new block, a new orphan block, we can reach something close to this equation here. And why does it matter for us here? Because mining is a random activity. The next block can be found in 1 second. It's just not that likely. So I'll just change slides here a few so I can give my point for you. On one hand, here we have that mining is a random process. So there's 22% of chance of finding a block in a quarter of the expected time. So let's see about Bitcoin. 22% of the blocks will be found in less than 2.5 minutes. And it takes 40 seconds to find the next block. So what's the likelihood that someone will find the block that will be orphaned after? After do some math, you can get to this equation. And this equation is important because the eta, the one dividing delta t, it's the average time to find the next block. And that's a parameter of the network. That's in fact the target of the DAA. That's the target of the difficulty adjustment algorithm. So the larger this value, Bitcoin uses 10 seconds, so 600 seconds. The less likely is to find an orphan block. The lesser this parameter, this time, this target of the DAA, the higher the likelihood of finding an orphan block. And it's a network, just like a blockchain network, it's all about incentives. Nobody's forcing or nobody is paying the miners to be there mining except the network. The network is paying rewards to the miners. And that's it. The network gives the incentives. And that's why handling orphan blocks is a very important matter. But besides the average time to find the next block, there's also the time to update an outdated miner. If we can reduce the time, then the likelihood of finding an orphan block decreases as well. And that's why in Hathor, we can use 30 seconds. In our next meeting, we will dive into Bitcoin and Ethereum and also Hathor, and you get a better understanding of every more factors that affect orphan blocks. Because remember, when a new block is received, if you come back here, before propagating the block to the network, the full node must validate it, must run the consensus algorithm, and those might be not that fast steps. Those steps affect the orphan blocks, the probability of finding orphan blocks. So in regards to designing a new blockchain, that's a very important parameter. The target of the DAA, of the difficulty adjustment algorithm, affects the probability of the orphan block, which affects the incentives of the network. Okay, so keep that in mind because that's really important. And the next question would be, okay, so now I understand how the mining business work, a little bit of it. I understand how the peers of the network are there. And I understand that after a best blockchain, that the network reaches a consensus out of the best blockchain. So why would there be multiple blockchains? Why do multiple blockchains happen? What causes them? Because miners have no incentive to do it. Okay, miners have no incentive. So who does? Why would it happen in the first place? And here, there are multiple reasons. Here I have some, so we can discuss. One thing that might cause the creation of new blockchains are network upgrades. So let's say that we create a new rule in our blockchain, and we change the definition of what the conflict transaction, we create a new feature. So we add something to the transactions. So outdated nodes, outdated full nodes running previous versions, they won't accept that transaction as valid. There's some noise in the background. Okay. Okay.
All on the internet, would you please mute your microphone?
Yeah, we have to mute them. Okay. So the outdated nodes, they won't validate these new blocks. So network upgrades are in a decentralized network, it's challenging. There are several techniques to do it in a safe way, but forks might occur. And we have some famous forks that happened on purpose, not because people didn't update, that are the creation of Bitcoin Cash. Ethereum had a fork into, I guess, 2018, and so on. So that's one cause. Wherever a fork happens, there are multiple blockchains. So different spheres will agree on different things. Another cause is the double spending attacks. And this cause is really important because that's what fears most exchanges. So let's say, and I'll give you some. I'll change the slide in a minute. But let's say that I deposit 10 Hathors to sell in an exchange. What happens is that first it goes to the mempool, and then it goes to the next block. Miners will try to mine it, and then let's say that it's confirmed. Let me just get back here. It's confirmed in this new block. Can the exchange safely confirm the deposit? Not yet. What happens? It's in the another block for the exchange. What happens if it's not there? So that's why exchanges wait. Each exchange has their own policy, but wait quite a few blocks before they confirm your deposit, because they're waiting to have a better consensus, something that won't revert, something that, and that's how confirmation happens, right? The more blocks we have after your transaction is confirmed in A3, the more blocks we have after it, that's the number of confirmation we say. So here we say that A3 transaction TX, it has 4 confirmations. So exchanges requires confirmation in order to accept your deposits. So here, let's get back to the double spending attack. What happens in the double spending attack? The attacker deposits something to the network. It gets confirmed by the best blockchain. And then they sell their tokens, they withdraw their money. And after they withdraw, they would like to cause a reorg. They would like to change the best blockchain to a different best blockchain where that transaction is not there. And they double spend. They create a conflicting transaction, TXB, and they try to put TXB in the new best blockchain. So they get their deposit back. They revert the deposit into the exchange. That's the double spending attack. And in this case, the attackers will be mining with a purpose. They're not looking for the reward mining. They're not looking for the fees. They're looking to get their money back and to trick, in fact, to steal from the exchanges. That's also called the 51% attacks, because usually to do this, the attacker must have a huge hash rate. And that's something that it doesn't happen. It's very rare. It's a rare event, but sometimes it does. It depends on the network, etc. But so intentions reorgs might happen because of attacks. Malicious things might happen because attackers are trying to exploit businesses that are running over blockchains. So double spendings might create new blockchains, different blockchains. And hopefully they won't be the best thing ever. Everything is safe for everyone. Another cause is a split brain. It's a natural thing. We have internet. Sometimes you try to open Google, it doesn't open. So you're not connected. Sometimes you try to open Facebook and it's not there. So you lost your connection. And it can happen with the blockchain network. What happens is that we call it a split brain when the network becomes 2 networks and they're not connected at all. Well, it might happen. Let's say that a country has a connection problem. The backbone, the internet backbone of a country is out for 10 minutes. All peers from that country will be in a separate network. They cannot receive and they cannot send blocks to the other group. And in this case, if this situation happens for a long time, miners from one of the groups, let's say group A, will find A4, but A4 will not exist on network B. So miners from B, they don't know A4, and they find B4. Even though X1, X2, and X3 are the same for both of them, because before the split brain, they were synced, everything was good, this situation might happen. Let's say that China decides to block Bitcoin for any reason, and they block for a while, and then the miners or the ones running full nodes, they must find a way to connect to the network again. It might happen because of problems, networking problems. It happened before with many countries getting disconnected somehow for some reason for a period of time. And after the networks connect again, they will share the blocks and reach a decision. And one of these chains will be voided. In fact, all chains except one will be voided, and only the best chain will remain valid. And that's important because exchanges and people doing business over blockchains, and you are building an application of blockchain, so you have to think about it. You must somehow ensure that you are connected to the right network, and you are connected. There's no split brain, and you are receiving the blocks, so you can trust that there won't be a reorg, at least not because of networking issues. Okay. Another cause of different blockchains to happen is an eclipse attack. What is an eclipse attack? So again, a blockchain is a network of computers all connected. So what happens when you run your full node? It will start connecting to different peers in the network. And usually you try to look for random selection of peers to be connected to. But you can be tricked and you can connect only to malicious peers. So let's say that I'm connected to these 3 peers and they belong to an attacker. In this case, see, my understanding of the blockchain is whatever they send to me. They filter, they work like a firewall. They control what I see. Whenever I find a new block or I try to send a transaction, they decide whether this transaction goes or not to the remaining of the network. So they control what I see. They can manipulate what's the best chain for me. They can skip sending blocks for me. So there are different policies to avoid this kind of thing. One of them is from time to time to change your peers that you're connected to. Some full nodes does it automatically. But yeah, the way the peers that you choose to connect to, it matters because it's fully decentralized. There's no coordination. So there might be malicious agents there. Malicious peers send you wrong information, trying to trick you. Okay, but it's really interesting that the blockchain is a zero trust system. Nobody has to trust nobody, anybody. There's no trust at all. You just, let's say that I'd like to connect a new full node to Hathor Network right now. I run my peer, it connects to the network. As long as I'm not in an eclipse attack, I'm not connected to malicious agents. I might be connected to a few, but not all of them, because the honest peers, they will relay the blocks to me. So I start downloading the blocks. And then some peers can send me B4. Okay, it's fine. Some peers of the network can send me C6. It's fine again. It's okay as well. As long as I receive A5, I'll reach my own conclusion. See, the network will never tell me A5 is the best blockchain. I'll make that conclusion myself out of the consensus algorithm. I'll calculate the work of each block. I'll see which blockchain has the highest total work, and I'll reach that conclusion by myself. So nobody trusts nobody. Nobody. And that's part, I guess that's the revolution thing, because you don't have to ask. There's no such thing as, I don't know, taking the average opinion of everyone there. Because in the internet, you can run as many nodes as you want. I can run 100,000 full nodes. I'm not mining, it doesn't affect the consensus. So I can't say that 30% of the network agrees on something. In this case, we are not talking about the number of people, but we're talking about the amount of work. We agree, all the peers in the network agree that the best blockchain is the one with most work, where people put more effort. It's not about how many people are there, it's about how much work has been done. And that's why it's a zero trust system. You connect there, you download, and you get to your own conclusions about it. Okay, that's exactly what exchanges do. They don't have to trust third parties. They cannot be tricked. And that's how your application should do. At the beginning of our conversation here, we were talking about an application and the blockchain. There's no such thing as a blockchain. We know it right now. And you don't have to trust anybody. Run your peer, run your full nodes, and trust your full nodes. Get the information, conclude yourself, take the conclusion, make the conclusion yourself, which one is the best blockchain, and that's it. That's how a blockchain works behind the scenes. And again, we get to the same question. What is a blockchain? And now you have a better understanding what these words means. A blockchain is distributed. All peers in the network have a copy of the blockchain. They even have copies of the voided blockchains. Sometimes they do, sometimes they don't. Usually networks don't relay voided blockchains, but you can have a copy. Networks are decentralized. There's no central point of coordination. Nobody is the owner of it. Nobody, that's why there's no such thing as, I don't know, someone asks Bitcoin to revert the transaction. There's no Bitcoin. There's no Hathor, because the network is public. The network is there and people, they just join and they do whatever they want. They can mine, they can just be there relaying transactions, it's free. And most importantly, it's decentralized. There's no owner, we are all the same in the network. And it's an immutable database because it's very expensive to make a change. So we consider it immutable. We consider that after quite a few confirmations, there's nothing else to do. It's confirmed, it won't be reverted. And that's how we can see a blockchain. Okay, and here I'd like to do a quick demo to show you how it might work. So let me, we still have some time, right?
Yes, yes. So just to tell them, so we will see a real creation of an NFT. So people are, there is a lot of, talk around an NFT. So he will create in front of you in real time a real NFT on Hathor blockchain, and you will see how does it work. Okay. Go ahead.
Yeah, and thank you. And I'll explain. We'll see everything that we discussed before will happen. In fact, it's happening right now. We'll just watch it happening, which is a very nice thing. So we watch everything happening. Before starting, I'd just like to see, is there any question there that I can help?
I think when you started to talk about NFT, people really moved to the rest of NFT.
Yeah, they'd like to see first. Okay, we can do this and go to the questions after.
So there is a question. Hold on, Marcelo. There is a question.
Okay.
He will explain it. Go ahead, Marcelo.
Okay. So what you're going to do here is that we'll create a non-fungible token. So let's understand what it means, what it is. So what we're going to do is that usually in our next meeting, I'll discuss how you can integrate and put information in a blockchain in details. Because see, note that we haven't discussed the details of a transaction. And why haven't we done it? Because then we need to be specific. We will discuss the details of Bitcoin, the details of Ethereum, the details of Hathor. So it's a specific discussion. Here for this meeting, we have a more theoretical discussion about the blockchain. And that's a generic discussion. Everything that we talked here is true for all blockchains around. We have thousands of blockchains. So we are not looking into the transactions yet, but next meeting we'll do this. And then you have a better understanding of a few things. But what are we going to do here? We are going to get a file, let's say an image, and we'll send that image to another network, not Hathor Network. And that's how usually people do with NFT. We send this image to a public network, just like a torrent system. But here we're going to use IPFS, which is a nice project. It's like a distributed file system. You can send files there and it will be there. After we send the file there, it's just for the file to be available for everyone to download it. The IPFS network will generate an ID of the file for us, a unique ID. And this ID, if you go to IPFS network anytime with that ID, you can see the file, the contents of the file. That's how it works. And then we'll get this ID of the IPFS network, and we'll put inside a transaction. That's our data. We put the ID inside the transaction, and we will write it to our full node. We will push this transaction to our full node. And then the full node will do its magic. It will validate, it will run the consensus and everything. And then it will relay the transaction to all the peers in Hathor Network. And the peers will receive the transactions, and the miners will start mining the next block, which will confirm this transaction. And here, I'm using a special thing from Hathor Network. Instead of creating a regular transaction, in Hathor Network, we have different types of transactions. I'll use a special one, a transaction that creates a new token inside Hathor Network. So I'll create a token for this class that will represent the file, like, let's say, the ownership of the file that I'm sending to the IPFS network. And that's what an NFT is about, usually. An NFT is just like a token, which represents ownership or some kind of ownership of a property, of an underlying asset, an image, a video, an audio, or some IP, some intellectual property, or it might be the shares of a company, whatever. So what we're going to do right now is that inside Hathor Network, we can create tokens, whatever, any tokens we'd like. We will create one token that represents the ownership of this file that we're sending to the IPFS network. And then after these tokens are created, we are free to send and receive the property. So I can sell the properties to someone else, and I can receive property from someone else. There's a lot of interesting NFT projects running in Hathor. I have some NFTs myself, and that's what we're going to do. And after writing, we want to read. I have here a full node running. So I'll just quickly show it to you. I don't know if you can see it. It's kind of very technical. It's the log of my local full node running. Can you see it?
Yes.
I've been receiving blocks, new transactions. That's the network coming, right? I received the new transaction. I did everything that we just discussed. A new transaction again. And then let me just.
Is he using Solidity or other programming languages? No, I'm not technical, but just curious.
What's the question?
Yeah. What was?
Are you using Solidity or other language like Python?
What is?
Oh, no. Yeah, we don't have Solidity in Hathor. It's a different piece. I'll give you the details in the next class, in the next meeting. But yeah, here we can just watch the network coming, and there's no Solidity here. Okay. The creation of full node in Hathor, it's a native thing. In fact, that's a difference from Bitcoin and Ethereum. Our basic transaction has a token ID that so you can create and use multiple tokens in one transaction. I'll give you more details, a lot of more details in our next meeting, because it's too much. I need to go into what is a UTXO model, what is account-based model, and how they differ and how it works. So yeah, that's the next meeting. So just trust me for now, and you'll get a bigger view next meeting. So what happens here? Okay. Yeah. Here we have these full nodes. It's a real-time full node. So new transactions are coming all the time and new blocks. So what I'm going to do after, we don't want to see like this, right? It's bad for users. So what we're going to do is that the full nodes is also connected to a public explorer, which is a web view, which gives us a page where we could go and we can see what's happening from the perspective of these full nodes into the blockchain. See, even when you go to a public explorer from Ethereum or from Bitcoin or from Hathor, it's not necessarily it's the truth. It's the perspective of the full node that's bringing the information. So there might be malicious public explorers showing you fake information. It might happen. So even though it's beautiful to have something really decentralized, it's very important to see who or why you are trusting into the information that you're trusting. Many people ask, if you're not mining, why would you run a full node? because and my answer is always the same, because you don't want to trust anyone. You don't want to have intermediates in the trust system, in the trust chain. You want to trust the blockchain. You want to trust the best blockchain, because that's what matters at the end of the day. So we're going to use here Hathor Public Explorer to see what's happening into the blockchain. And we'll see our NFT there. So I'll open here our Explorer. Again, we are looking from the perspective of one full node. Here we have the latest blocks and the latest transactions. Okay, I can open a transaction. I can see what's happening. This transaction is confirmed by a block, as you can see here. We'll go very deeply into these things in our next meeting. I'm just giving you a short explanation so you understand the NFT part that we're going to do right now. Here I have some information about the network, the peers, the synchronization process, where they are, the version they're running, and all the things. And here, what are these peers? The peers connected to this one. I can change the peers, and I can change the list of connections we change. Each peer is connected to a different set of peers, as we just saw in this conversation. So what I'm going to do right now, you don't know yet what is a wallet, the technical explanation of a wallet. We'll see it next meeting. But here I have a wallet. I hope you can see it. This wallet has a balance of 4.96 Hathors. And that's Hathor Wallet Desktop for macOS. This address represents my wallet, so I can send and receive funds in this address. And what I'm going to do is that I'll go for custom tokens. And here I have the choice to create an NFT. And it does everything for me. Right now, I'm not going to explain exactly what it's doing behind the scenes, but in our next meeting, we'll dive deep into it. You understand every bit of what's happening in the transactions. And here, when I click to create an NFT, I have to fill up this form. It's a very simple thing. There's no solidity, no programming, nothing here. The network handles everything for me in this case. So now I need a file. And maybe, I don't know if I can do this here at Zoom, but I'll try to get, if you allow me, all the cameras are closed except for Carlos. Is it okay, Carlos, for me to take a screenshot? Would you like to close your camera, or is it okay to have you on the picture?
No, you can take my screenshot. I'm good.
Okay, so everyone that's is comfortable with being the picture, you can open your cameras. I'll take a screenshot of us and I'll create an NFT out of it. Okay. Hello, everyone. It's nice to see your faces. Okay, there are more people coming. That's nice. Wow. Okay, so let me do this. It's nice because this picture will be in the blockchain forever. It's very nice to think like that. It will be immutable. So just took a picture here. Let me get the picture. Where is it? It should, oh, okay, there it is. Let me just resize this. And here is our picture. So I'll take this file and I'll send this file to the, let me get back to the presentation so I can explain to you. I'll send this file to the IPFS network. To do this, I'd have to run a peer, a full node from IPFS, but I'm not, because I'm going to use an open a service for a company called Pinata. They allow me to send files to, so I'm trusting Pinata here. It's my intermediate, and I'll just click here and I'll upload the file. Let me just get the file here again, and I'll upload the file for Put it here, MIT class, November 13, uploading. And now Pinata is sending, is receiving and confirming this. Pinata is not a blockchain, it's a different animal, but yeah, they're putting the file in the network and the file will be available there. And it will give me an ID. A unique identifier of this file in the network of Pinata. And that's the file, that's the ID. This thing here, QMVKZ, it ends on FZA9. If I click on the image, I can see it, and it's already there on the IPFS network. So I'll copy this ID, I'll go to my Hathor wallet, and I put it there. IPFS, because I'm using IPFS, and I'll put it there. So let's create a token out of it, right? So short name, nice blockchain class. Oh, Hathor class, blockchain class, Hathor is the next one, MIT. And the symbol, BCM. I don't know. How many tokens am I going to create? Let's say that, how many people do you have here, Carlos? I can send you the property of this NFT. I can send it to you.
Let's put 10 people. Just
Around, how many? 10?
Yes.
Okay, and then the people in the NYU. So let me create, I don't know, I'll create here 100, and I can send to after. I'll create a meld authority, which means that I can destroy the remaining tokens if I want. So just, we're the ones, we're gonna have access to this. And then I'll hit create, I'll put IP. And what it's doing right now, it's creating the transaction and sending the transaction to the full node. And it was sent. The transaction is in the network right now. I can click here and I can go to the public explorer. And here is our transaction in the network. The transaction just appeared here as well in the full nodes. My full node just received it. It's fast. But it received from the network because my wallet is not connected to this full node. So now that this transaction is there, see, confirmation level 0. There's no transaction confirmed this transaction yet, no block. It's in the mempool. Let me refresh. Oh, it's confirmed. A block confirmed it. Just like we said, a block picked the transaction from the mempool, was mined. This block was mined. I'll go there, I'll explain to you and confirm this transaction. And here, you don't know what inputs and outputs are yet. We're going there next meeting. But here, we have the data stored in our blockchain. That's the IPFS ID. We cannot change it. If we change this letter from X to Z, then the hash of this transaction would change, and then the block would be invalidated. And then the whole blockchain must be mined again until you have a new best chain without this transaction. And trust me, you can't do this because our hash rate is too high. Okay, and if, let me just get this transaction ID here. Just give me 1 second. If I go to the token page here, you can see that the NFT is here. The image is here. It's in the blockchain forever. It will be there 1 year from now, 10 years from now. And there's 100 tokens that gives ownership for this image. And I'd like to send these tokens for you. So if you want, you can install Hathor wallets. Just send me your address and I'll send you the token. And it's yours, just like it's mine right now. It's on my wallet. If I go to my wallet here, I can see the token here, blockchain class MIT. There's just one transaction in this token. Here is the configuration of the token, some administrative tools. I have melt authorities, I can destroy tokens. And if I go to the list of NFTs, well, let me just reopen my wallet. It should be there. Just reopening. Let me bring it to your screen. My wallet is running, and there it is in our list, in my list of NFTs. Okay, so let's go again to the Explorer. You can send me your addresses in the chat if you have, and I'll send the token for you later. Or now, if you send me, I just can't find where the chat is right now. I'm just looking for it.
I believe, Marcel, that people, okay, Jan has one address, but here in the classroom, we still don't have a wallet. We will create it.
Okay, you can create you can message me, you can email me your address, and I'll send it to you. Okay. And then you can send to the students after. I can send to you, Carlos, or they can send me directly. I can send to them. But what's important here is that the information was encapsulated in a transaction. This transaction is valid. It's in the best blockchain, and it's confirmed by this block. Let's go to the block. That's the block. The block confirms several transactions. Here, Hathor has a different structure, so we can see all the transactions confirmed by this block. But what matters here is that the height of the block is the number of the block in the chain. Block 1, block 2, block 3. That's block 1,900,000. So, and more blocks are coming every 30 seconds because of the DAA algorithm. And the weight here is the difficulty, the mining difficulty. In Hathor, the math is pretty simple. The number of attempts to mine this block, is 2 to this power. So the whole network together right now, just I guess you can see my screen. I'm just opening a calculator here. The whole network right now, just to find this block, it made a work of, I don't know, that's a huge number. That's the number. That's the number of attempts. I cannot read this number out loud. So that's the number of attempts to find the solution for this block. And that's why it's safe. Just for comparison, my computer can do in a CPU around 1 million attempts per second. 1 million would be like here. This 9 is 9 million. My computer cannot find the solution for this block, not by itself. It's unfair to put into the CPU. Usually people have ASICs and different stuff to mine, but that's how it works. So here, we just created this NFT. It's in the blockchain. Let me get back here. And what happened was exactly like this. Pinata did the work for me in the IPFS part. It generated the ID for me. It was encapsulated in a transaction. It was written in our full node, pushed, as we say, pushed to the full node. The full node relates all the other full nodes in the network, all the peers in the network, and they received it. We haven't mined it. So in some of these peers, there was a miner connected, and the miner found the next block. And this block, but our transaction was in the mempool. So our transaction was included in the block, and the block confirms our transaction. And that's why it's in the best chain. It's in the best blockchain. And when we go to the public explorer, just like we did in the web, to see how it works, to see the NFT, to see this information that we're looking here, we are trusting this full node that's bringing information for us. In this case, my company, Hathor Labs, is running the full node for us. So I trust the full node, but you don't have to. And I'd say that you shouldn't trust anybody. Blockchain is about not trusting. If you'd like to have information, run your full nodes and get information for it. So you don't have to trust anybody. And that's why it's beautiful. That's why you have full nodes in different countries, people doing different stuff, and nobody can say no to them because they are free to connect. That's how it works. And it's just a taste. In our next meeting, we'll really deep dive into Bitcoin, Ethereum, and Hathor. You understand all the specifics. What is a transaction, how it works, what is there, what is it bytes, and it will explain a lot of decisions made by each network, why the networks work as they work, and how each decision affects the network, affects the scalability of the network, affects the confirmation of the network, and a lot of different stuff. So next time we won't talk in an abstract level. We'll talk in a very specific level. So we'll dive deep into, just to show you one slide here, we'll dive deep into Bitcoin. We'll dive deep into the modeling and how it works inside the transactions. And for a taste of it, I have this video that we developed for Hathor some time ago. And it's a 3-minute video. It's a very short video. And you can see a taste of how Hathor compares to the Bitcoin architecture and to Ethereum. Let me just open it here. Okay, ads.
We cannot hear
I
you.
guess you can't hear, right? Yeah. Weird. How do I do to send you my audio?
What?
He needs to stop sharing and then share again and click on share audio.
Oh.
Okay. Where do I do this?
You need to stop sharing.
Okay. Stop sharing. Stop sharing.
Share again the video.
Share again. Share audio. That's great.
Share audio. Exactly.
Thank you. Just did it. Oh my gosh. It asked me to install an audio device, Zoom audio device. It's installing right now.
Marcelo, can we get access to your slides to share among the students? Hello?
Yes, you can. Sure. Can you hear me?
Yes. So can you?
Sure.
Later on, can you send me these slides for me to share with our students?
Sure. Yeah, I'll do this.
Okay.
It's installing here. Oh my gosh, it's not working. Let me try again.
It's not a big deal, Marcelo, because we have the link of the YouTube video and anyone will be able to play by him.
Yeah, maybe. Yeah, I can send it to you. Yeah, we are at the end of the class here. Yeah, my audio is not working. I didn't know that I'd have to install this plugin. I don't know why it's not working. But yeah, you can see this video later. It's a nice piece, and I can also play the video in the beginning of our next meeting, so we start from it. But it's just a teaser for what we're going to discuss in our next meeting. I don't know, maybe Carlos, maybe you can share your screen and play if your sound works on sharing. Let me just unshare my screen. Just a second. Stop sharing. Okay.
I don't have. Can you send me the YouTube address over the chat?
Oh, I got many addresses here. Okay, I'll send you the links. Let me send you, Carlos, the link first. Just 1 second. Here is the link, Carlos. There it is. To everyone, here's the link. While you do this, okay, you're opening. Go ahead. I'm not sharing. Okay, so you can share. Thank you very much.
So I don't have the sound either. So yeah, We need to play it by ourselves, Marcelo. The sound is not going on.
Okay, yeah, that's a nice animation that shows. Let me just get the screen back, and just to give you some. In fact, we don't need the whole video. Can you see my screen, Cam?
Yes.
Yeah, here we show the video explains exactly what we said. When a transaction is created, it's sent to the mempool, and then the blockchain. There's the blocks of the best blockchain, and then a new block is arriving, and how it works, validates, and etc. And how Hathor does it differently. So different understanding of the structures. So it's a technical piece. Here, the block is being propagated to the full nodes, and the full nodes repeat the same steps. The video can explain way better than I can here. So yeah, we can watch it later. And just for the end here, of course, I'll open for the questions, but I'll just do it so you can see. I just got some nice some addresses here. So I pick one. I'll send our BCM token to this one. I'll send one. Everything is happening again. My data was encapsulated in a transaction. The transactions was relayed to the network, and I just sent to ping you zoo. And probably it's in our wallet right now. It's already there. And if I click here, I can see all the transactions of the token and etc. Let me, yeah, that's it. So I guess I sent one for this address. The transaction is here, and it's already been confirmed by a block. Wow, that's fast. It entered in the next block. So that's really nice. Your transaction is confirmed, and I cannot take your token back. It's yours. There's nothing I can do. And basically, that's the end of it for today. So at Hathor, we are hiring. We want the best people. So if you'd like to join in this adventure, just send a message. Here we have some screenshots on the top, the founders, my friends Jean, Pedro, and Jean, and on the back, that was part of our team right now. So, but it's all everything is remote. But yeah, it's very nice. We could take this picture. We are bigger than that, and so I'd like to, of course, open for questions. But thank you very much for being here, for viewing, and for hearing all these technical things. Thank you very much.
Marcelo, thank you again. I will stop recording right now. Thank you. We had a lot of fun. So thank you very much. And I'll schedule with you the final section for us to better understand how blockchain works.
Thank you very much. And I really appreciate the opportunity, Carlos. Thank you very much.
Thank you. Bye-bye.
Yeah, thank you. And just one thing, I don't know if people are still here. If they, of course, I'm open to questions right now. You can send me questions. And if they have any other questions, they can just email me and I'll be happy to answer it. But if you have any questions there, I'm open to it. I have some time here.
Thank you, Marcelo, again. Questions from your side?